Article 392 of the National Electrical Code, or NEC, specifically addresses cablebus. Within Article 392, Section 392.14 focuses on ampacity. Ampacity refers to the current carrying capacity of a conductor, typically expressed in amps. This section provides guidelines and requirements for determining the ampacity of cablebus systems, ensuring that they are appropriately sized for the intended electrical load. Cablebus is a specific type of electrical distribution system consisting of insulated conductors mounted within a ventilated enclosure. It offers an alternative to traditional conduit and wire systems, particularly in industrial and commercial applications where flexibility and ease of installation are important. Several factors influence the ampacity of a cablebus system. Firstly, the size and type of conductors used play a crucial role. Larger conductors generally have higher ampacities due to their lower resistance to current flow. The type of insulation material also affects ampacity, as some materials can withstand higher temperatures than others. Secondly, the ambient temperature surrounding the cablebus affects its ampacity. Higher ambient temperatures reduce the ampacity of conductors, as the heat generated by current flow is dissipated less effectively. The NEC provides correction factors to adjust ampacity ratings based on ambient temperature. Thirdly, the number of conductors bundled together within the cablebus enclosure influences ampacity. When multiple conductors are bundled together, their heat dissipation is reduced, leading to a lower overall ampacity. The NEC provides adjustment factors to account for conductor bundling. Fourthly, the ventilation provided within the cablebus enclosure affects ampacity. Adequate ventilation helps to dissipate heat, allowing for a higher ampacity rating. The NEC specifies requirements for ventilation openings and spacing to ensure proper heat dissipation. Section 392.14 of the NEC outlines the specific requirements for determining the ampacity of cablebus systems. This section refers to all the relevant NEC articles and tables that provide detailed ampacity ratings for various conductor types and sizes. It also includes provisions for adjusting ampacity based on ambient temperature, conductor bundling, and ventilation. When designing and installing cablebus systems, it is essential to consult Section 392.14 of the NEC to ensure that the system is properly sized and installed in accordance with code requirements. This will help to prevent overheating, insulation damage, and other potential hazards. The NEC provides comprehensive guidance on the safe and effective installation of electrical systems, and adherence to its requirements is crucial for protecting people and property from electrical hazards. In summary, Section 392.14 of the NEC is the primary source of information regarding the ampacity of cablebus systems. It provides detailed requirements for determining ampacity based on various factors, including conductor size, insulation type, ambient temperature, conductor bundling, and ventilation. Consulting this section and other relevant NEC articles is essential for ensuring the safe and reliable operation of cablebus systems. The ampacity of a bus drop cable, as covered in NEC Article 392, is a critical parameter for ensuring safe and reliable operation. Bus drop cables are typically used to supply power from a main busway to individual loads or equipment. Understanding how to determine the appropriate ampacity for these cables is essential for electrical engineers, contractors, and inspectors. Article 392 provides comprehensive guidelines for cablebus systems, which include bus drop cables. The ampacity requirements are primarily found in Section 392.14, but other sections may also be relevant depending on the specific installation conditions. The first step in determining the ampacity of a bus drop cable is to identify the conductor type and size. The NEC provides ampacity tables that list the allowable ampacities for various conductor types and sizes based on their insulation temperature rating. Common conductor types include copper and aluminum, each with different ampacity characteristics. The insulation temperature rating indicates the maximum temperature the conductor insulation can withstand without degrading. It is crucial to select a conductor with an appropriate temperature rating for the operating environment. The ambient temperature surrounding the bus drop cable significantly affects its ampacity. Higher ambient temperatures reduce the cable's ability to dissipate heat, which lowers its allowable ampacity. The NEC provides correction factors to adjust the ampacity based on the ambient temperature. These correction factors are typically found in NEC Table 310.15 bone or similar tables. It is essential to consider the maximum or expected ambient temperature in the area where the bus drop cable is installed. The number of current carrying conductors in a raceway or cable also affects the ampacity. When multiple conductors are bundled together, the heat dissipation is reduced, which lowers their allowable ampacity. The NEC provides adjustment factors to account for the number of current carrying conductors. These adjustment factors are typically found in NEC Table 310.15b3 or similar tables. It is important to note that neutral conductors that only carry the unbalanced current from other conductors are not typically considered current carrying conductors for this purpose. The length of the bus drop cable can also affect its ampacity. Longer cables have a greater voltage drop, which can reduce the voltage available at the load. The NEC recommends limiting the voltage drop to 5% for feeders and branch circuits. If the voltage drop exceeds this limit, the conductor size may need to be increased to compensate. The installation method of the bus drop cable can also affect its ampacity. Cables installed in free air typically have a higher ampacity than cables installed in conduit or cable trays. This is because cables in free air have better heat dissipation. The NEC provides ampacity tables for various installation methods. The ampacity of the overcurrent protection device protecting the bus drop cable must be equal to or less than the ampacity of the cable. This is to ensure that the cable is protected from overloads and short circuits. The overcurrent protection device can be a circuit breaker or a fuse. In addition to the general ampacity requirements, there may be specific requirements for bus drop cables in certain applications. For example, if the bus drop cable is installed in a hazardous location, it must be suitable for that location. The NEC provides specific requirements for electrical equipment installed in hazardous locations. It is important to consult with a qualified electrical engineer or contractor to ensure that the bus drop cable is properly sized and installed in accordance with the NEC and other applicable codes and standards. Failure to do so can result in electrical hazards, equipment damage, and even fire. In summary, determining the ampacity of a bus drop cable involves several factors, including conductor type and size, insulation temperature rating, ambient temperature, number of current carrying conductors, cable length, installation method, and overcurrent protection. Article 392 of the NEC provides comprehensive guidelines for cablebus systems, including bus drop cables. By carefully considering all of these factors and consulting with a qualified electrical professional, you can ensure that the bus drop cable is properly sized and installed for safe and reliable operation. Bus drop cables are a common component in industrial and commercial electrical systems, providing a flexible and efficient way to distribute power to various loads. Understanding the ampacity requirements for these cables is essential for ensuring the safety and reliability of the electrical system. The National Electrical Code, or NEC, is the primary source of information for electrical installations in the United States. Article 392 of the NEC specifically addresses cablebus, a type of electrical distribution system that includes bus drop cables. Section 392.14 of Article 392 focuses on the ampacity requirements for cablebus systems, including bus drop cables. Ampacity refers to the maximum amount of current that a conductor can carry continuously without exceeding its temperature rating. The ampacity of a bus drop cable is determined by several factors, including the conductor size, insulation type, ambient temperature, and the number of current carrying conductors in the cable. The NEC provides tables that list the ampacities of various conductors based on these factors. To determine the ampacity of a bus drop cable, you must first identify the conductor size and insulation type. This information is typically printed on the cable jacket. Once you have identified the conductor size and insulation type, you can consult the appropriate NEC table to determine the base ampacity of the conductor. The base ampacity is the ampacity of the conductor under ideal conditions, such as an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit, and with no more than 3 current-carrying conductors in the cable. If the ambient temperature is higher than 30 degrees Celsius or 86 degrees Fahrenheit, you must apply a temperature correction factor to the base ampacity. The temperature correction factors are listed in NEC Table 310.15 Bone. If there are more than 3 current-carrying conductors in the cable, you must apply an adjustment factor to the base ampacity. The adjustment factors are listed in NEC Table 310.15 B3A. The final ampacity of the bus drop cable is the base ampacity multiplied by the temperature correction factor and the adjustment factor. It is important to note that the ampacity of the bus drop cable must be equal to or greater than the load it is supplying. If the ampacity of the cable is less than the load, the cable may overheat and fail, potentially causing a fire. In addition to the ampacity requirements, the NEC also specifies other requirements for bus drop cables, such as the minimum size of the cable, the type of insulation required, and the method of installation. It is important to consult the NEC to ensure that the bus drop cable is installed in accordance with all applicable requirements. The NEC is a complex document, and it is important to have a thorough understanding of the code before installing any electrical equipment. If you are not familiar with the NEC, you should consult with a qualified electrical contractor. Here is a breakdown of key considerations for bus drop cable ampacity, referencing the National Electrical Code, or NEC, specifically Article 392 on cablebus and Section 392.14 on ampacity. Firstly, conductor type and size are paramount. The NEC provides ampacity tables, like those found in Article 310, that dictate the allowable ampacity based on the conductor material, such as copper or aluminum, and its cross-sectional area, measured in American Y-gauge or AUG, or circular mils. Selecting the correct conductor size is crucial for handling the intended load current. Secondly, insulation temperature rating is critical. The insulation surrounding the conductor has a maximum operating temperature. Common insulation types include THHN, THWN, and XHHW, each with different temperature ratings, typically 75 degrees Celsius or 90 degrees Celsius. The NEC ampacity tables are based on these temperature ratings. Ensure the selected insulation is suitable for the installation environment and the conductor's operating temperature. Thirdly, ambient temperature plays a significant role. The NEC ampacity tables assume a specific ambient temperature, usually 30 degrees Celsius or 86 degrees Fahrenheit. If the actual ambient temperature exceeds this, a correction factor must be applied to reduce the allowable ampacity. These correction factors are found in NEC Table 310.15 Bone. High ambient temperatures can significantly direct the cable's ampacity. Fourthly, the number of current-carrying conductors matters. When multiple conductors are bundled together or run in close proximity, the heat dissipation is hindered, leading to a reduction in ampacity. The NEC provides adjustment factors in Table 310.15 B3 to account for the number of current-carrying conductors in a raceway, cable, or bundle. These adjustment factors can significantly impact the overall ampacity. Fifthly, installation method is important. The way the bus drop cable is installed affects its ability to dissipate heat. Cables installed in free air typically have a higher ampacity than cables installed in conduit or enclosed spaces. The NEC provides different ampacity tables for various installation methods. Sixthly, voltage drop is a factor. While not directly related to ampacity, excessive voltage drop can affect the performance of the connected equipment. The NEC recommends limiting voltage drop to 5% for feeders and branch circuits. If the voltage drop is excessive, a larger conductor size may be required, which can also increase the ampacity. Seventhly, overcurrent protection is essential. The bus drop cable must be protected by an overcurrent protection device, such as a circuit breaker or fuse, with an ampacity rating that does not exceed the cable's allowable ampacity. This protects the cable from overloads and short circuits. Eighthly, specific requirements for cablebus systems apply. NEC Article 392 provides specific requirements for cablebus systems, including bus drop cables. These requirements cover aspects such as construction, installation, and support. Ninthly, dirting factors for specific equipment should be considered. Some equipment, such as motors, may have specific dirting factors that must be applied to the bus drop cable ampacity. These dirting factors are typically specified by the equipment manufacturer. 10thly, working with a qualified professional is recommended. Electrical installations should be performed by qualified electricians or engineers who are familiar with the NEC and local codes. They can ensure that the bus drop cable is properly sized, installed, and protected. Remember, always consult the latest edition of the NEC and local codes for the most up-to-date requirements. Understanding and applying these principles is critical for ensuring the safe and reliable operation of bus drop cables.